Senior Director of Engineering, leading the Architecture and Technology Group in ARM India. Ms. Aparajita ma'am has a career spanning over 22 years in the semiconductor industry in the areas of processor and system architecture, design and verification. She is responsible for working with ARM's architecture partners and the ecosystem partners to ensure the ARM-based systems in the market are compliant to the ARM architecture. Ms. Aparajita ma'am holds a master's in computer engineering from the Ohio State University and an MBA from the University of Texas in Austin.
Introducing our next guest, Ms. Apurva Verma ma'am, Senior Regional Manager, ARM Education, India. She has 23 years of experience in the education management space with a master's in sociology and business administration. She started her career in 1997, followed by managing various initiatives in the K-12 space, which included creating an employability program for the physically challenged. In 2011, Ms. Apurva ma'am moved to the higher education space, focusing on bridging the academia-industry divide, enhancing student employability, and creating an entrepreneurial ecosystem for youth. She was involved in conceptualizing programs for tech institutes and universities, managing content creation focusing on experiential learning, and implementing these programs across India.
Now, I would like to invite Ms. Aparajita Bhattacharya ma'am on stage to give a seminar on exploring ARM technologies and opportunities. Please give a round of applause. Can you switch the swap this please? Can't do it there. Need to swap the displays there so that you don't see this view, right?
They can see that. Only this only will be visible. Just check it once.
No, it's
1 minute.
they are seeing
Okay,
the top map, so I need to swap the displays. Yeah. How do you? Yeah, just go to that and is it?
After doing this one,
have a Zoom or something?
Zoom.
Ah, okay. Swap displays. All right, we figured it out. Sorry, thank you for your patience. I know what I'm competing with right now. It's just past lunchtime, so all of you have had lunch, and this is called the graveyard shift, right? So yeah, hopefully I'll keep you awake for some time. I won't bore you a lot, but I'll tell you a little bit about ARM today, and the latest buzzword today is AI. So touch upon that, but really demystify it a little bit, right? Because we all tend to hear AI and AI. So here I am. Let's dive right in. So this is going to focus a little bit on different aspects, right? I'm going to give you a little bit of introduction to ARM because now you do have a course on ARM architecture, so you do know what ARM is. A lot of times we have to talk about who is ARM. A lot of questions used to be around, we don't know who ARM is. So I'll give you a little bit of introduction. Since you're learning the architecture, it'll be good for you to know ARM's footprint, right? So very brief, introduction in that sense. A little bit of introduction to the ARM architecture. This is not intended to be, in any sort of depth. This is going to be a little bit about evolution and just a little bit of sense on how it has evolved over the years, but not really digging in deep. So don't ask deep down technical questions. I'm not going to answer them. And then a little bit on the technology trends, and then overall evolution of the architecture, technology, what spaces we work in, right? So just a little bit of history. ARM started way back in 1990, and it was a joint venture across 3 companies, Econ Computers, Apple, and VLSI Technology. From 1993 onwards, the ARM processors got into smartphones, the mobile phones and smartphones. You can say that whole generation of smartphones kind of, fueled ARM's growth, made the, architecture get into a lot of sets. And I would contend that every one of you who has a phone here, there is ARM technology in there. So 99% of the world's smartphones run on ARM architecture. And then today, literally from sensors all the way to high-performance computing, supercomputers, they use ARM technology. And you'll kind of get a sense of that as I go through the talk, right? So another thing that's quite popular right now, cloud computing. You would think, ARM in smartphones, that's where, ARM architecture is, but no, we have gotten into cloud computing. So you would have seen some of the announcements which have happened in the recent years. You've heard of the Graviton processor. That is ARM architecture. That's designed with ARM's processors. So there are a lot of cloud providers that are looking at sort of the total cost of ownership and what it costs them to kind of build with ARM architecture and build with ARM technology, and it's making a lot of sense. The other thing is the pedigree of ARM is to do with power efficiency, right? So we pride ourselves on being power efficient, look at energy efficiency as a metric. So be able to kind of really talk to that space, because if you knew most data centers, the biggest cost for them is really power, right? It's in cooling all those different machines. So there's a lot of cloud providers today pulling for ARM. And because now the spaces, I talked about ARM getting into sort of the higher end systems. So Fugaku, that's the supercomputer in Japan, that has ARM, that's built on ARM architecture. And a lot of buzz about the NVIDIA GPU and CPU, so Grace Hopper. So the Grace CPU is ARM based. Hopper is their GPU, but Grace Hopper, that combination, Grace is the ARM CPU. Then you also have the other end, which is 5G and carrier. That's all the things that are using the mobile networks and making it easier for us to connect anywhere, anytime. That we have solutions in that space as well. And then getting down to really the edge devices, the IoT, the low power, where power efficiency is super important. That's where ARM architectures will. So if you look at kind of the whole spectrum. It spans all the way from, low-end little sensors all the way to, supercomputers, and with cloud computing in between and lots of things in between. There's another area where there's a lot of innovation going on. You would have, think about it, autonomous driving, right? Automotive industry, that's something that is definitely, getting a lot of traction. We have a lot of companies that are kind of innovating in that space. And if you look at it, few things that are quite important in that space is functional safety. So being able to depend on things not breaking down, having redundancy. So those sort of technologies require, a level of redundancy, a level of, security, and a level of making sure that everything is done right, and there are no breakdowns or last-minute surprises. So there's a whole transformation in that space as well, especially when it comes down to sort of building in, a lot of trust in your autonomous cars. Anyway, that's a space that's still innovating. It's not that it's done. We will continue to see a lot of traction, a lot of growth in that space as well. And there are some numbers, I'm not going to go through everything, but there's a lot of industry pull for ARM that there is in that space as well. And then I talked a little bit about IoT. IoT is about volume. There's a lot of volume. There's tons of sensors. Whatever you try to do today, there are so many sensors around that sense, the environment, sense things around. And if you look at some of the numbers, there's millions and billions of ARM processors, tiny processors that really are in that space. 90% of wearables powered by ARM SoC. So, I would contend that all of you have touched enough ARM so far, right? All right. Okay, this is not. So I talked about this compute solutions from sensors to servers, so I won't belabor here. But there is a lot of emphasis, not just on performance, but also on efficiency, power management, a lot of solutions that need different things at different power points. Okay, so, and this is just giving you a sense of how many ARM processors are out there. This kind of tracks from 1991, when ARM was formed, all the way, we hit 1 billion in a decade, and then kept just exponentially growing to the point that the latest numbers released right now is we have 280 billion ARM processors out there in the world. So that's a staggering number. That just gives you a sense of, how much is out there based on ARM architecture. So what you're studying is sort of, you're kind of equipped to kind of look at the future and say, there's so much technology out there. I keep doing this, okay. All right. So let me talk a little bit briefly on the ARM business model. So this first part is going to be a little bit more about ARM. So just bear with me. It gives you a sense of, where we come from, what our legacy is, and where we're trying to take it. So ARM is an IP provider. We develop technology and license it to semiconductor industries, right? So traditionally, ARM has not made chips. It's been a technology provider working very closely with the ecosystem, with our different partners. We have architecture partners, people who pay ARM money to have the license to use the ARM architecture, which is like, you can think of it like blueprint, right? We give them the blueprint, and they design their processor based on the rules that are laid out in that blueprint, right? So that is ARM architecture. And so those architectural licensees pay us to have the rights to build an ARM processor using the ARM architecture. And then we have our silicon partners and OEMs. There are companies, semiconductor companies, that licenses IP. So ARM internally also designs processors, and that is put out as a product offering. And we have semiconductor companies that license ARM processors and build their own SoCs. We also have solutions where we build, more of a subsystem, a compute subsystem, and also license that to partners. And then partners take them into implementation, and then take them out to foundries and build chips, right? So there are two ways in which ARM does business. One is when we license, we get a license free. And for every chip that ships out, we get a royalty. Right? So it's two-pronged kind of method of how ARM does business. And there is all this business development because we are creating pull at the end from the original equipment manufacturer, OEM customer, to say what technology is needed for the solution, for the problem that they're trying to solve. And then, the more valuable problems we solve, the more sort of our technology gets in there, and then that results in sort of our technology being in every chip, and then that results in a per chip loyalty. So this is in sort of nutshell, this is the ARM technology model, business model really. And then if you look at it, what are the key ingredients of market leadership? It's having this table of things, right? So you start like at the base, you say, well, I have an architecture that I can offer to the world. This architecture is used to build processors and system IPs, and then they can take it and build SOCs and provide solutions to partners, right? So like I said, we have the ARM architecture. We have CPU IP. So this is processor IP that ARM designs. But at the same time, the ARM architecture is used by our partners to build their own CPU IPs as well. So it's sort of orthogonal in some sense. And then we have physical IP, which is about the implementation, right? This is about the logic gates and things that you do to actually put down the gate level implementation of the RTL that is written for CPU and system IPs. And then you have system topologies. The creativity really is in building differentiation through different systems that you build for solving various problems. You have very different problems to solve in the mobile space, where most important thing in mobile is, anyone wants to take a guess? What's the most important thing in your mobile? Processor. So processor. So that means it's your responses that come back, how fast they come back, how quickly you do that. What are other considerations? You have to be louder, I can't hear. Other considerations? Does your phone run out of juice? Does, right? So power. Power is one thing. You want day of use. You want to make sure that you do have that all day, all on. I can use it how I want, and it stays alive. It doesn't break down on me when I'm stuck somewhere. I'm trying to order my taxi to come, and I can't because I'm out of battery. So those considerations are also there. So we have to think about what is the need at that point in time, and for that system. You don't worry about that with your laptop, right? Not so much, I would say. So the considerations for a laptop are slightly different. Then you go to sort of your cloud computing and servers and all, very different considerations, right? Their battery is not important, but maybe what is important is power dissipation. What does it take to actually keep that data center cool? Am I spending all my money trying to keep that data center cool? But there are many other technologies, which I'll talk about a little bit later, right? Where some other things come in which would become important there, maybe not in your phone so much, right? And then finally, of course, hardware is just a piece of brick, right? It's nothing without software. So you need software that then provides the use cases, the applications, the enablement that can enable to use your hardware. So this is sort of, it's across the entire spectrum of what all the things you need to worry about. Also now let's talk a little bit in detail on the whole life cycle. This is sort of the technology life cycle, right? When you see a product in the market, what has been happening is more than 5 years ago, we have thought about that. So architecture and research, like research side architecture, this all works, literally I would say more like 7 years ago. So whatever products you hold in your hand today, that has been thought about and planned for 7 years ago. That's when the first thinking about, what new features are needed, what is the trend, what is it that we need to enable. Speech processing, if you think about it, or new forms of gaming on your mobile. These things, if we didn't think about it, 5-7 years ago, you wouldn't have something that could enable it or something that would make it faster or more capable of running today. So that thing starts way back. And what does it start with? It starts with specifications. It starts with enough collateral such that the designs can be verified. It starts with lots of good documentation, because you want your entire ecosystem to be thinking about software that is going to use all these hardware features. You can put ton of hardware features into anything, but if you can't harness it, if you can't work with that, then it's just a piece of brick, right? So you have to be thinking of what else it is. Second thing, you have to align the entire partnership, the ecosystem. You want to create pull for your product. So for that, you have to, when we think of an architecture feature, we are actually working with the partners today, saying, where do you see this going? Or do you see that there is value in this? Or sometimes they come to us and say, hey, this is what we would like you to build. So we get input from the partnership in terms of what are some of the architectural features we should put in. And then we have to align the entire ecosystem, make sure that there is software out there that is ready when the products get to market. So there's a lot of work that happens ahead. Then you have the, once all these architecture development and all these things and creating this pull from the market comes, we get into the product and solution development. And yes, there is some overlap and things like that. It's not exactly neat and little silos, right? We're always cross-working. There's a little bit of shift left, which happens on product side as well. So that's where the actual IPs get built. Your processors get designed, your systems get built, your SOCs are formed, your chips get done, and then it gets into actually a product space. Then you have the outbound marketing, those sort of creating pull in the customer's mind. Because at the end of the day, you are all the ones buying the phones. You are the ones that are buying the laptops, right? It has to come straight from here. And if you're thinking about cloud computing, then it is the data center people who have to see, yes, there is value here. I'm going to, book all these orders or whatever it is, right? So all that happens. And then finally, light of day, you see it like, from time today till 5 years out, then you actually see the products in the market. So this is really, the whole kind of, I would say, technology life cycle, from the germination of an idea all the way down to a product in your hand. And one more thing, I've been talking architecture. Just want to draw a distinction between architecture and microarchitecture, because even when new joiners come into to our company or in general, right? A lot of people get confused about what is architecture, what is microarchitecture, right? And architecture really is a set of rules. It's a contract. It's a contract between the hardware and the software, such that the software can depend on the hardware behaving a certain way, right? So this is, you have so many different layers. You have the hardware, you have firmware, you have software. How do they talk to each other? They have to talk to each other in a language that is understandable across various layers, right? So that is really what you call the architecture. It's a set of rules that bind the hardware and bind the software. Software will then be written in keeping with the rules of the architecture. So that is architecture. And microarchitecture is really, sort of the implementation of it, right? So, for example, I'll talk about generally a processor, right? So instruction set, how you add two numbers, what are the rules around adding, what happens on overflow, what flags need to be set. That is architecture, because those are rules. Software will know, okay, if there's an overflow, I know I can go and look at this flag. If there's an exception, I should go and look at this register. Those are architecture. Okay, building a new branch predictor, or increasing your issue queue, right? Or the decision to build caches. What kind of associativity does it have? These sort of things. These are microarchitecture. Why? Because they're specific to the processor. You can take the same architecture and you can build very different processors out of it. Okay? So that is the difference between architecture and microarchitecture. Hope I've been clear. I mean, do you guys are clear about what is the difference between an architecture and a microarchitecture? Fair? Yeah? Are you awake? All right. So yeah, so there's there's architecture, microarchitecture, and implementation that I talked about is actually the laying down of circuits, right? It's libraries, it's circuits, it's what you take to foundries and then get it to build, right? So that's sort of the overall definition, and this is more a pure computer science kind of definition, so just making sure we all, okay. So yeah, so what do you mean by, what is architecture? What do we actually generate, right? So if you look at it, if you look at ARM, we have 3 profiles of architecture. We have application, real-time, and microcontroller. These are distinct architectures because the needs of the market are very different. Application processes feature rich, it is for your smartphones, it is for your laptops, it is for cloud computing. It is all, everything has to run a rich operating system, things like Linux or Windows on ARM. These sort of things where there's a lot of features in the software that need to be taken care. Real time, what is important is braking systems. It's in the automotive space, right? Braking systems, real-time responses, right? Over there, failure is not an option, right? You don't want you slam the brakes and your car refuses to stop. No, I don't want to be in such a situation. So that's real-time. And then microcontroller, it's the industrial little things, the little sensors, and so you have more, more of a, micro variant. It is not feature-rich at all. It is more to do with, bare bones functionality, keeping the power envelope in mind, right? And these are, again, these architectures are all used internally. We have the Cortex line of processors. We have Neoverse, which is the sort of high-end processors that go into big server systems and all. And again, licensing I did talk about. And I talked about one of the things that we do is ensure compliance so that we keep the compatibility across implementation. So any software meant for an ARM architecture should be able to run on any implementation, right? It doesn't matter if ARM builds it or ARM's architecture partner builds it. Should be able to run it, because otherwise what you'll have is software fragmentation in the whole ecosystem. So we want to avoid that, so we kind of do a lot of work around this compliance space where we're actually writing a lot of verification collateral so that partners can run it and sign off, right? And then there's system architecture, which is more open license. So this is not licensed like CPU architecture. This is more to do with SOCs and software standards. It's a lot about standards and open source. So that there's a lot of ecosystem that's developing. So you think about organizations like Linaro. They do a lot of open software standards. So ARM will be working with them to ensure that wherever we put our systems out, they are taking and leveraging all the open source work that is happening across the globe. And again, there's a lot of differentiation in this space. This is where partners differentiate because they're creating solutions for various markets, various segments, and things like that. So yeah, this is a little bit about that. Okay, we're now moving sort of to the next section of the presentation, which is more to do with technology trends. So a lot of you are aware, the biggest buzzword nowadays is AI, artificial intelligence. Everything seems to have that in there. So artificial intelligence in every device. You have autonomous machines. I talked about autonomous driving cars, but other than that also there's a lot of autonomous enablement happening, a lot of robotics there, lots of warehouse solutions that are being created. So there is a lot of autonomy and intelligence being built into various things in the industry. Other thing is augmented reality. This whole sense of experiencing sort of a metaverse kind of thing and AR, VR, all these different things are a big thing today. And then, of course, there's the hyperscale, cloud, and connectivity. But across all of this, the other themes, so all these themes mean there is a lot of compute required. There's a lot of new applications. So thinking about what features will work in those spaces. What do we need to build, to be able to take advantage of those trends in the industry. And then at the underlying base of it all, you need good security, because security and privacy, these are big concerns, right? Especially if you think about artificial intelligence, there is more fear, right, on what this is and what this is going to do to sort of the human factor. So there's also this security and privacy thing. Now, I said one of the things I would do is sort of demystify artificial intelligence, right? If you look at artificial intelligence as this big universe of artificial intelligence, it's the general intelligence given to a machine to be able to do the sort of intellectual tasks that a human being does. So it's like teaching machines to think. That is artificial intelligence, right? And how does it happen? It happens by sort of training the machine. So machine learning, that's a way to introduce artificial intelligence into, a system. So you have to do machine learning, make the machine learn. And as they learn, they think, right? So that is what machine learning as a subset. And deep learning is a little deeper. So you have lots more layers, a lot of nuanced understanding. You're going deeper rather than broader, right? In that sense. So these are sort of, I would say, the different layers of artificial intelligence. Now, if you think of classical programming, how did it work in the past? You would have some input data. You would give some rules to the machine. And what you would get out of it is answers, right? So you're telling the machine, here are my input data sets. Here are all the rules you have to apply, and here's the answers that you get. So what is different now? What is artificial intelligence doing to this world? Well, there are no rules. So we are not telling the machine what the rules are. We're telling them, here's your input data, here's your output data. Go figure out a way of what rules you need to apply so that, the input data gives the output data. That is the difference. That's the difference between classical program and machine learning. Did that kind of make sense? This is what is happening now. Do I hear yes? Did you get what's the difference? That your rules and data in classical programming giving you outputs. Here your input and output getting in there to tell you what the rules are. Which means this part is called training. You're training the machine to how to think. What are the rules that I need to apply? Then the next step comes inference, which is then you give the machine input data, and it would have already figured out the rules because you've trained it, right? So now it can produce you output because it's figured the rules out itself. So that is what is called machine learning, right? So this is sort of demystifying. It's a very simple way of looking at things. There is a lot of complexity in this. If you're really interested in learning more, go with this book, Deep Learning with Python, by Francois Chollet, whatever. But yes, it's a good book. These diagrams are pretty much in his first chapter. You should just, look it up. Okay. So little bit, again, I'm taking you back in time, a little bit of historical evolution of the ARM architecture. Started out really simple, right? Early 1990s. ARM v4, a long time ago. We're now at v9, I'm just telling you. So v4 is where we started. There was the thumb instruction set. Slowly, we kind of evolved, got a little bit more, ARM v5, ARM v6. These were all smaller things, smaller microcontrollers, small scale processors, nothing of the types of what we have now. And then came ARM v7, which was introducing a lot of the big ticket features, right? We had added virtualization, we added large page addressing, there is vector processing, and SIMD. SIMD is single instruction, multiple data, but I'll talk about it a little bit more. But I'm just introducing some of the terms. There's a lot of, alphabet soup here. Just bear with me because it doesn't come into one diagram otherwise. And then ARM v8 was the 64-bit architecture. So ARM used to be 32 bits, 32-bit architecture till ARM v7. And ARM v8 is a 64-bit architecture. By the way, these slides, you will find them online also. They're all open material. So, don't take notes if you need to. You'll find them all online. There's a ton of material there. But ARM v8, it introduced, it's all backwards compatible, by the way. So full compatibility. We introduced lots of new features in there. This is just to give you a sense of how many different things we're working on. So vector extensions were introduced, improve virtualization. So when you go back to ARM v7 advanced SIMD, that was the start of sort of vector processing capabilities in ARM, right? And why I'm going to talk about vector processing a little bit is when we talk about training the machine, right? We talk about big data sets and things like that. What are they? That's a lot of math and a lot of vector math. So at its core, You'll have a lot of this AI, machine learning, all these things. But you just have to understand at the very core of it is mathematics. No, not rocket science, this is mathematics. Your basics are matrix multiply. All your vector processing is nothing but matrix multiply. Once you get a hang of that, you can design solutions, right? It's only adding layers of capabilities on top of your basic fundamentals. So nothing, no magic there, right? You get your basics right, you can design anything. So I just want to get that message across, right? Focus on the basics, everything else follows. So yeah. And then, so ARM v8 is what we introduced in 2011. Now that's a long time back. Then came ARM v9, which was sort of what's right now, what's hot and heavy in the market right now. So ARM v9 gave a lot of emphasis on sort of what we were seeing as future workloads, so machine learning, and more DSP capabilities, and improved security. All the trends that I talked about, these were things that were getting anticipated at that time. Hey, this is what we need to work towards. These are the things that are going to be important. That's what it was. So, looking at, so what was v9 doing? v9 was extending the vector processing capability. Things that were introduced in v7, strengthened in v8, but taking, sort of giant leap forward in v9 for, machine learning workloads, digital signal processing, and all these XR, as in, augmented reality, virtual reality, all the different metaverse trends and things like that. So let's talk a little bit about the scalable vector extensions. So what was so interesting about this was that if you look back at sort of vector architecture in the past, right? It used to be fixed on a vector length. The vector length was 128 bits. You could only do 128-bit vectors. But now, with scalable vector extensions, you got this new paradigm called vector length agnosticity. So basically, you could write software programs, targeted. You could just write a software program. And then that program would be capable of running on hardware that was vector length agnostic, which means you didn't have to recompile your program. The hardware could be, sort of supporting any vector length. It could be 128 bits, it could be 256 bits, anything between 128 bits and 204 bits. In increments of 128 bit is how you could build your vector extensions in the machine. But what this did was a big boost for software, because what software developers hate most is I write a program, you have a new machine in the market, now I have to recompile my software, I have to rewrite my software for your new hardware. So this capability that was given was the ability to kind of introduce this vector-like agnostic programming such that it would adapt to the hardware, right? So this, and then the whole scalable vector extensions, this was actually a partnership between ARM and Fujitsu. And what they built, they were looking at the Fugaku supercomputer. And it was in the top 500. It was actually the #1 supercomputer in the world at one point of time. It was built with ARM architecture and some of these, the SV extensions and things like that. So this is what sort of, I would say, catapulted ARM into the, era of sort of high performance computing. And what does this do? This helps your, scientific workloads, climate modeling, vaccine research, ocean currents, materials research, lots and lots of applications in the high performance computing space. And these sort of, capabilities of doing these kind of scalable vector processing gives a big boost to such workloads. So this sort of, so this was introduced in v8. There's another part of it that's now in v9, but we went in v7 from vector processing of fixed 128 bits to the scalable length vector processing to in v8, and it's called SVE. All right. So now, basically SVE evolved in v9 and became SVE2, sort of next generation of SVE. And here it added capability for machine learning and data processing. So original application was mostly meant for high performance computing space, right? It was very focused that this is where we need to be. So not that every instruction was made sort of the SVE2 enabled, but the next generation of SVE said, we have to take the same capability and then push it downwards as well into the machine learning space and all that, because that can speed up all your machine learning algorithms and compute that is needed in that space as well. So lots of different features that got added in. So when we say Neon, what is Neon? Neon is your first advanced single instruction multiple data capability, advanced SIMD that we talked about in the ARM v7 architecture, same one. But there's a lot of detail. I will send some maybe recommendations in terms of if you want to learn. There are some really nice resources out there if you want to learn more about ARM, okay? So just talking about SV2 in a broad sense enables broader capability and vector performance for all of ARM world's programmers, not just a HPC space, and then it scales with the vector length. All right. So now, very quickly, we'll come to sort of the other aspect that I was referring to, the security aspect. Now, as you kind of try to see, where the world is going, there's a lot of, coverage on cyber crimes. Everything is connected. There are so many attacks going on. And how do you really secure it? So this is seen as something quite important in terms of security, right? So let's look at some of the security solutions. In V9, we had this confidential compute architecture. And I'm not going to go into details of layers and things like that. I'm just going to explain the concept of it, right? So if you think about, let's say, a cloud computing paradigm, right? You have things that are running in the cloud. So there is a layer called the hypervisor layer that is taking care of scheduling and shifting workloads and being able to manage all the compute from various different clients. So many people are running in the cloud. It's not just one person. They have multiple clients. Everybody has their own application. So what's happening there is there is somebody who manages. Now the fundamental thinking about ARM confidential compute is the fact that because there's so much distribution, right? Everybody's running, workloads shift, things shift. There is a lot of trust we need to build, right? That our data is safe. It is not spied upon, hacked into, things like that, right? So it starts with this whole principle of something that manages your workload has the right to manage, but not the right to access, right? So it's sort of like a blind thing. It can help you manage the whole process. It can help with scheduling threads, taking out threads, running, providing all the resources for you to run the thing, but it should not be able to spy inside. It should not be able to get to your data. It should not be able to hack your program. So that is the fundamental isolation technology that is being introduced in ARM confidential compute, right? So it introduces, there are a lot of terms like realms and isolation technologies and things like that, but that's what, overall it is. So these are details. I think I'll just skip over this for now. But where are all the applications? You have driving systems. You don't want anyone hacking into your driving system. You have medical data that is super sensitive. You don't want anyone accessing it. So these are all sort of the different applications that benefit. And then there's cloud computing, like I talked about. You want some entity to manage it, but you don't want them to access the data. That's the thing. So we talked a lot about architecture. Very briefly, I'll talk about some of the other steps. I think architecture and then CPU IP. I'm just going to touch a little bit on implementation because there may be some of you that are interested in sort of the implementation space, the hardware logic gates and things like that. So basically, if you look at the whole ARM physical IP space, physical IP means physical implementation side of things. So you have, again, different markets. And each market has a different requirements. I'll just call out a few things, right? In terms of if you look at networking and servers, what's important is, it should always be online. It should have high fault tolerance. It should have a long lifetime. It should have continuous operation. So the corners for which it is designed is very different from, let's say, something that is ultra low power. It should be very low cost in ultra low power, low voltage. It doesn't need that kind of performance, but what it should do is really not consume that much power. So the corners for which these are designed are very different. The technologies that are used are very different. So you have, mainstream, sometimes you have high-end, those sort of things. So I just wanted to give you a sense of the different kind of work that goes on in a physical IP team, right? They are working on libraries, they are working on designs, they are building optimized designs and looking at where they need to build for and what are the needs in that, and accordingly design, pick the process, pick whatever features they want to put in. Sometimes go for premium, sometimes go for low cost, those sort of things. So there are a lot of these trade-offs that happen when choosing what you build with. And then there's a lot of work that happens directly with the SOC and EDA partners. So when ARM's team sort of designs these implementations in the physical sense, they are working with all the top EDA companies that you see here. They are working on various steps in the whole implementation cycle. It goes from creating simulations and looking at those simulations to actually doing synthesis, doing a place and route, running your design rule checks and timing and doing timing analysis and static timing analysis and things like that. And then it gets into this physical IP block. And then that finally gets pulled down to the foundry and then gets built out as a chip, right? So there is a lot of, this other focus is that, it's very expensive to build silicon. You don't want silicon to come back dead, right? So you have to take a lot of care in designing such that you build first time right silicon. Or you have ways in which you can revive chips and things like that. So you have to build for robustness, making sure that they don't come back dead, right? Process complexity is rising. Also the complexity of where the geometries are shrinking, and there's again lot of work happening in those fronts in looking at new options, new processes, new materials, new technologies. So a lot of work goes on in that space. And then of course the time to market, so that you are working very closely. If you miss a shuttle, that's a problem. You cannot miss it, so you have to make your deadlines. You have to keep to your timing that you were aiming for, this sort of thing. And then, not to forget, the most important thing that I had also talked about, we talked a lot about hardware, but software is another important, very, very important thing, because that's what runs on your different processors. It's what makes that piece of hardware very useful. So look at sort of the various layers of complexity in software. I'm just calling it the architectural hamburger, but there's a lot of things, right? At the very base, you think of it as reference design platforms. On top of that, you have firmware. Then you have virtualization, which is helping manage that. Then you have the kernel, Linux kernel. You have different options for the kernel services. You might have real-time operating systems, RTOS, which works on the R-profile processors. Then you have performance libraries that help accelerate your applications. So you have software and performance libraries. And on top of everything sits applications. So it's really a little like an onion. There are so many layers in there that you have to take care of all these different things. So look at all the different pieces. So firmware also, there's so much variety. There's different kinds of file systems. There's so many tools you can use. So this is just giving you, and this is just, I would say, the top of the iceberg. There's so much below, right? So this is just giving you a little bit of an overview sense. And then what do? We open source software at ARM is a big thing. We actually develop an upstream open source software for the ARM architecture so that we are ready and we are sort of keep that pre-ready such that when hardware hits the market, there's already applications out there, there's already software out there that can work with it, because you cannot stop to develop software for hardware that's already ready. So a lot of this work happens in the background. So in the end, I'm just trying to put it all together. The whole ARM ecosystem is, you start with architecture, you build CPU and systems, there's software that enables it all, there's open source, where there's a lot of things happening in the ecosystem itself to enable all what's coming in through the hardware. There's partners whom we work with, and they play a major role in kind of building that thriving ecosystem. And then finally, you have the products in your hands. And that's a culmination of all these different activities that happen at various stages all throughout. With that, I'll close my talk. Thank you all for your patience, and yeah, hopefully it was useful. Thank you.
Anyone who has any questions can ask ma'am their questions and clear their doubts.
Hello. Okay. Although it's been asked multiple times, like, why do we need to study about computer organization and architecture? Although it's been answered uniquely each time it's been asked, so I would like to ask you, why is it necessary to study about computer organization, architecture, and microprocessors, please?
Sure. So again, I think it's a layering of all the different things you start learning. You start learning starting from math, right? Maths is logic, like, adding two numbers, getting to decimals, getting to quadratic equations, getting there. So it's about a layered approach, right? And then what do you do with that knowledge is now math turns into binary logic. Binary logic is nothing but, power of 2, you have zeros and ones, and that is a binary arithmetic part, right? Now, computers understand the language of binary arithmetic. So then now you have, much more complexity built on top of that basic principle of binary arithmetic. What computer organization teaches you is just that what have people done with that to kind of organize, because a long time ago it was very much, very physical, very this thing, but as things scale, the need for organization comes in. The need for, how do you manage storage? How do you manage memories? You just don't have, different, just addresses randomly. You want to organize those addresses. You want to make it easy to access. If you think about add, there are so many variants. It's not just adding two numbers. When you add two numbers, what happens on overflow? What happens when you do add and do something else with it, right? You want to put more capability into that. Because if you look at the fact that we are building more complexity in less area, and that's Moore's law, like scaling every 18 months, we have added so much hardware that we keep adding capabilities. But at the basic level, just learning, okay, what is the basic of a computer? That helps you to get a leap start into the whole, okay, do I understand the basics of a computer? What is logic? What are the various stages? How do I organize things? So that's just a base. You can call it foundation. And learning an instruction set. Now there are so many instruction sets. It's not just ARM. ARM is one of them, right? So you do have the other instruction sets that are in the ecosystem as well. So it is one sort of language, if you will. It's the language of computers. So, think about it as when you learn speaking languages, right? You will start with alphabet, then you will start with words, you will start with sentences, then you'll, have complex ideas come out because you know all the basic. So it's very similar. You start with math, you understand the basics of math, you get to a point where you're learning a little bit more organization, and then getting to the point where you use that and then build upon it. So they say, right, we all will build on our past. So building on the shoulders of giants, lot of innovation has been done. And then we have to find a place where we can connect and then take it forward from there. So this is basically your foundation when you kind of learn of computer organization approach. And this we've been learning for years, right? Even when I was in college, I also learned, computer organization basics. I started right there, And so I don't think those principles have changed in all these years. Yes, the applications, the more complexity has come in. You probably learn much more advanced concepts because that's something that is today in the textbooks. You can read it, you can learn it, you can understand it. I talked about one of the deep learning textbooks. All this wasn't there when I was in college. So yeah, hopefully that sort of understand is just, I would say, building blocks. Keep learning. You can always learn more. Yeah.
Thank you.
In starting, you talk about NVIDIA using ARM and other thing. So what is the scope of ARM processor in making powerful GPUs and other?
So ARM does have solution in GPUs. It's called Mali. I did not add it in here. I did have a slide on that. But we do have graphics processing units as well, Mali. So that's ARM solution for GPUs. It's already there. Actually, if you're interested, go on and read a little bit more about it as well. I just mentioned the fact that Grace Hopper was a ARM NVIDIA kind of, collaboration, if you will, right? Because Grace is based on ARM processor. The Hopper is their solution of GPU. But yeah, ARM solution is Mali. Yeah.
Probably what he's asking is
Huh.
that Mali is good for mobile phones. And
Correct.
everything.
Yeah.
Is there any product which would compete with the high-end NVIDIA processor or AMD
Yeah. That's right now it's just still in that space as well, right? If you look at currently the Mali solutions are in the mobile space. Yeah, I can't speak of forward roadmaps right now. Yeah, sorry. But at a fundamental level, what I'll say is yes, that technology does exist within ARM. Yeah.
Good afternoon, ma'am.
Good afternoon.
Ma'am, I want to ask one thing. Are we somewhere near in expanding ARM processor into servers
Yes.
or desktops?
Yeah. So the whole, if you look at most of cloud computing and all, we already have ARM solutions in there. So Amazon's Graviton processors, they're ARM based. I think we did have announcements recently as well on different cloud computing providers having ARM solutions in there as well. So already, yes, ARM processors are already in the servers. Not nearly the same volume as some of the other incumbents in that space, but there is a lot of pull, there is a lot of traction with ARM in servers. Yeah.
Thank you, ma'am.
Yeah, the question is regarding the security of ARM. Right now, a lot of companies have this trade-off, right, where if they want to prioritize security, they have to lose some other resources, just a simple trade-off. So how much does ARM, the future of ARM, maybe version 9, tend to address that issue of reducing the trade-off between security that product might have?
So security is pretty much something we take very seriously at ARM because it is ever increasing in volume. So if you look at sort of security in an architecture solution, we had the confidential compute that has just been announced. So that will be in sort of the implementations that build V9. We'll have confidential compute as the security solution, right? Which brings in isolation technologies, which is about isolating different applications from each other, right? So one application does not peep into another, or the one that manages several applications does not leak data across applications or be able to itself spy on applications. So that in fundamental level, that's a sort of security solution by ARM in the architecture. Then in terms of product itself, we have security security in the life cycle of development of the processor, in which the specifications themselves, we carry out security analysis of the specifications. The teams build security-oriented tests that test and try to find those holes, which if there are any holes, we tend to kind of figure out where those holes tend to be. So a lot of testing is done around security itself. So yes, I think security is taken quite seriously at ARM. Especially if you also think about automotive space, there is a lot of security there. You don't want external hacks, things like that. So there is a whole product security team and things like that. So they do engage with all the different developments.
So can we say like at a hardware level, we can test the security as well?
We can to some extent. We can where all the sort of, so looking at product specs, you can look at, what are the attack vectors, what are all the different things that might be used to do side channel attacks, or, so we have teams that look at that and look to mitigate those attacks. So they look at, various side channels, they look at, here are all the threats that might come to fruition, right? So we do have those teams looking into it. We also have some security I would say databases where we kind of